So I wanted to pick up where I was there, and what I had done in the morning was introduce the general idea of optical response of solids, introduce some of the kind of higher level formalism that make these kinds of the kinds of analysis we do and how we kind of start to think about the problems. What I'm going to do now is give a number of kind of snapshots of various different projects, both the ones that I've been involved with and ones that I haven't been, but I've been particularly enamored by. I'm going to give you, this is going to be constructed in, I'm going to talk a little bit about techniques and give you examples of different techniques that we use, and in so doing, introduce some physics associated with that, and then give you some more explicit examples of physics and of particular kinds of material systems, and then more examples which are kind of more, if you will, organized by phenomenology and less by material systems themselves. So let me just continue. The thing I was mentioning about techniques was this particular setup that we've done a lot of work with in my lab that we call a Corbino microwave spectrometer. And Corbino, the terminology comes from Corbino as a particular geometry used sometimes in doing quantum Hall measurements. But here it is just a coaxial waveguide that we terminate a sample at the end of the coaxial waveguide. And if you will, the sample is kind of a donut geometry. And in the field of transport, this is called a Corbino geometry. Okay. So this is data I just showed you. Now I want to show a little bit about some other things here as well. Should I point? I think I'm just going to stand in front. So this is measurements from the Corbino geometry of a thin film superconductor. So it's indium oxide. It's the real and imaginary parts of the conductance. So conductivity in 2 dimensions has units of inverse ohms, so it's a conductance. So here it's a 2-dimensional superconductor which undergoes a particularly interesting phase transition. So red is warm, blue is cold. Now, when I wrote down earlier the Rudabeh model, just to give you some very rough intuition as to what's going on here, when I wrote down earlier the Rudabeh model, what I had was sigma NE squared tau over m times 1 plus I omega tau over 1 plus omega squared tau squared. And I want you to consider what happens, right? So this looks like some Lorentzian, and then, not like that, more like that, let's say, the conductivity versus omega. And I want you to just consider as a cartoon of a superconductor, at this point it's just a cartoon, what happens when tau goes to infinity. Okay, so that's the momentum dissipation time goes to infinity, and you can imagine what happens here. As tau goes to infinity, this Lorentzian gets sharper and sharper and sharper until finally, let's say, it goes to the limit where it's a delta function. This peak here becomes, let's say its maximum is pushed to lower and lower frequency, until finally, in that limit, we have a delta function in the real part, and then in the imaginary part, so let's say that's sigma 1, and this is sigma 2, and it's proportional to 1 over omega. Okay, so this is the canonical response at low frequencies for a superconductor. It's a delta function in the real part, it's a superconductor, but the imaginary part is large, 1 over omega, and of course we can never measure, we're interested in the strength of this delta function, meaning let's say its area, its integrated area, but we can't measure this directly. If we try to do a DC resistivity experiment, we just see 0 resistance. So it's really the imaginary part where the interesting stuff happens, 1 over omega. Okay? Now, let's look at what happens in the superconductor here. We're going to talk about superconductors in different contexts, but the thing I want to concentrate on is first at high temperatures, which in this case is 3 degrees Kelvin, meaning the normal state. This flat line that's kind of buried under here, that's the normal state. And so we're talking about this film is a disordered superconductor. If you were to ask what's its scattering rate, its normal state scattering rate of the electrons in the normal state, it's let's say 100 terahertz. So it's super disordered, something very, very large. Okay? So there's the real part, and then there's the imaginary part. And the imaginary part is just down here, and you can see all of this kind of fuzz. That's experimental noise. Just because there's all of this noise doesn't mean it's a bad experiment. It's a good experiment because you have to realize this is on log scale, and there's 7 orders of magnitude of conductance being measured on it. So you put something on log scale at the lowest frequencies, eventually you'll see something. So the point is, in the normal state, the imaginary part is small, and the real part is just flat. Okay? Now, we cool it down, and we go towards the superconducting state, and what happens? The thing I want you to note is, in this plot here, as you cool down to lower and lower temperatures, as we go to lower temperatures, these curves are becoming enhanced. There's a maximum, which moves through the spectral range, okay? And as you go to lower and lower temperatures, that maximum moves to lower and lower frequencies. And somewhere in here, I've labeled the curve which is closest to TC as this dark black line. Probably TC was just infinitesimally below that. Now remember, in a superconductor, the conductance goes like 1 over omega in the imaginary part. So this is on log-log, and so power laws show up as straight lines in a log-log plot. And so this kind of flat straight line here, that's the 1 over omega dependence of the low temperature state. The thing I want you to note is as we come and march down towards the superconducting transition temperature, there's this maximum which forms. What you're seeing there, essentially in the raw data, are superconducting fluctuations. So there are superconducting fluctuations. We can think of these kind of heuristically as these kind of bubbles of evanescent superconductivity kind of forming, holding on for a moment and then dissipating, and the material becomes better and better conductor. These bubbles form for longer and longer periods of time over longer and longer length scales until eventually, let's say the time scale turns to that of, diverges to the length of a PhD thesis, and that's the superconducting transition. Here, this is, if you will, can be plotted in units of inverse PhD thesis, its frequency, and so what you see is this maximum directly represents critical slowing down of these fluctuations as you go to the superconducting state. So critical slowing down is a phenomena that's associated with continuous phase transitions, the notion that near a continuous phase transition there's some kind of intrinsic time scale. And as you go closer and closer to this transition, whether it's a classical transition like this one or whether it's a quantum transition, there's some kind of there's some kind of internal dynamics, and they're going slower and slower and slower and slower and slower until finally the time scale diverges, and then that's the transition. So you're really seeing that right here, and you can see I've labeled this curve, which was my independent measure of where TC is, but it's probably, actually TC was just infinitesimally below that, okay? Now, this is a 2D superconductor, and two-dimensional superconductivity has some interesting properties. First, go back to this cartoon of the superconducting transition itself. Again, the imaginary part, or say the real part of a superconductor has this delta function with a particular coefficient in front where it's n over m. N over m is the density of carriers divided by their mass. There's some constants of nature. The imaginary part, you can see, goes like 1 over omega, again, with these constants of nature that are in there, okay? And so the point is, by measuring the imaginary part, we can actually measure the delta function. Okay? Now, 2D superconductors have superconductors in general, and particularly superconductors that have fluctuations. And a very important quantity in trying to understand the fluctuations of superconductivity is a quantity called the phase stiffness. Now, we can think, of say a superconductor or superfluid has some kind of macroscopic wave function that we might write something like this. Okay? And in the low temperature state, the system is such that this phase, if there's no currents in the system, the low temperature, lowest energy state is where this phase is everywhere uniform all over the system. Now, if you have any continuous elastic medium, whether we think of say a piece of rubber or a spring, or in this case a phase field, any continuous elastic medium, you can write down the energy of deformation of that medium, generically speaking, as the square of some kind of generalized coordinate, right? So it's Hooke's law in the most, in the simplest sense, the deformation of a spring. But this is kind of, if you will, true in general, right? Spring, rubber, concrete, et cetera, has this particular form. And it's true also for this case of the phase field. So if I imagine, for instance, some superconductor which is maybe continuous in space or is perhaps granular, where there's a bunch of pieces where the phase lives on each piece of the superconductor, and each piece of that superconductor is coupled by some kind of Josephson coupling, I can write down a model. Again, this is just Hooke's law, 1/2 times some stiffness of the spring times some generalized coordinate squared. This is just the energy of deformation of that phase field. Okay? Now, in a superconductor or superfluid, if I have a gradient in the phase that corresponds to a velocity. So in different language, this gradient in the phase field, square, right, which is potential energy language, corresponds to nothing other than the center mass kinetic energy of the superfluid itself, right? So I can just equate these two guys, and it turns out then that I can solve for the stiffness coefficient T, which you'll see is n over m times a constant of nature, which is just this thing we're measuring here, except for the 1 over omega dependence, right? So the takeaway point is that the imaginary part of the conductivity allows us access to this energy scale, which is the phase stiffness. Right? And so that's been a very important kind of putting data in this language has been very important for understanding fluctuation phenomena in superconductors. And here, kind of, you could say explicitly, let's say I'm writing it here in terms of conductivity, we can in general, by kind of constructing some units of quantum of conductivity, constants of nature, we can construct a relation for this T theta, which is going to be this phase stiffness. Now we're going to be measuring at finite frequency, and that has a particular consequence. Now in a 2D superconductor, one of the things that one might expect is a particular kind of transition which is endemic to 2D XY type models, which is called the Costal-Brezinski transition. And this has the very interesting feature that if you plot the superfluid stiffness as a function of temperature, okay, superfluid stiffness, what I mean is this phase stiffness, let's say measured at 0 frequency, right, where this delta function, what I'm saying is the strength of this delta function plotted as a function of frequency. So as you warm up, it may come down for some particular effects. The Costal-Stallis prediction is that the superfluid phase stiffness, or the superfluid density as it's sometimes called, will happen at a universal, the transition itself will happen at a universal value, which, let's say the Costal-Stallis transition temperature happens at a value which is predicted by the value of the stiffness of that value. Okay? So this was first shown nicely in mixtures of helium-4, helium-3 films, but is also kind of a general way of understanding superconductivity. So what you would expect then, if we plot this dashed line as the Costal-Stallis condition in some particular units, and you would say warm up your 2D superconductor, perhaps the superfluid stiffness would come down until it would hit this line, and then there's this catastrophic proliferation of vortex-antivortex pairs, and the superfluid stiffness may just drop to 0. You could imagine another superconductor where you prepared it in some other fashion, and it would follow a line like to here, and then it would drop to 0. Okay? That's if you were measuring at 0 frequency. Okay? You can't really measure truly at 0 frequency. And a consequence of measuring at finite frequency is, when you're measuring at finite frequency, is that the finite frequency essentially sets, in the context of this problem, essentially sets a length scale over which you're probing the superconducting dynamics. Okay? So, if you will, if the dynamics of the vortices are diffusive, then this is the particular relation that one expects. And so kind of the intrinsic length scale that you're probing the system by is set by this kind of diffusive relation where it goes like 1 over the square root of omega. Right? So if I probe at very low frequencies, I probe over very long lengths. If I go to higher frequencies, I'm kind of probing the existence of superconductivity on short length scales. And this should sound reminiscent of what I was just telling you about in terms of the looking at seeing critical slowing down in the system. Okay, so a cartoon of what we would expect if we would go to higher and higher frequencies is you kind of go to higher frequencies, which means shorter length scales, and then you can see the kind of underlying superconductivity, which is still there. When the Costal-Stallis transition happens, this means that you got this vortex-antivortex pair proliferation on long length scales, and that's what you would measure by using a very, very, very low frequency probe. Okay, so that's the cartoon. That's the actual data that we measure in our Corbeto geometry setup. So this is the superfluid stiffness measured as a function of temperature, measured at different frequencies. Okay, so blue is at the highest frequencies, and something of order about 15 gigahertz, and red goes down to very low frequencies. This dashed line is the Costal-Stallis transition, and you can see these curves start to splay off from each other right exactly where it matches the dashed line. Right? So this was kind of the first real evidence for, let's say, 2D XY superconductivity in a thin film of a superconductor. And there's a whole interesting story about it. We have a whole paper on this, but there's this interesting story that's associated with basically scaling phenomena near this, what is nominally a 2D XY classical critical point. If there's questions, please. I'm just going to kind of start going through different examples of different phenomena. So if there's questions about individual aspects of the physics, please just let me know. So a technique that we actually use quite a bit in my laboratory is a technique what's called time domain terahertz spectroscopy, or terahertz time domain measurements, if you will. And what we do in this experiment, there's supposed to be a movie here, which is unfortunately for some reason not playing. What we do in these experiments is we use a laser, and oh, there's actually what happened to this? It's supposed to be playing. No. Okay, there's a better view of what's going on. Good. Okay, good. So we use ultrafast laser, which is coming in here. This is producing at 80 megahertz. This laser pulse is then propagating around the table. And I'm not going to talk about all the details of this, but so the laser comes in here. It goes through a beam splitter. 2 pulses propagating around the table. The laser here creates a pulse of terahertz radiation. We could place a sample at this position right here and measure it. And then the laser helps us in detecting the pulse of terahertz radiation. It's called time domain terahertz spectroscopy. The way it works is the following, is that there is a device, it's called an Austin switch, after Dave Austin, which was the inventor of it. It is, this is a picture of 2 of them. And this is a piece of gallium arsenide with some electrodes on the surface, which have a gap between the electrodes of about 5 microns. So this structure is biased by about 20 volts. And its resistance is something like, let's say, 20 or 30 mega ohms. So 20 volts across 30 mega ohms does nothing. So it sits there. But then you come in with a laser and you zap this thing, and the resistance of the switch drops from, say, something of order about 20 mega ohms to something of order a few hundred ohms. It's biased by 20 volts. And charge races across this gap and jiggles on the scale of the electron-hole recombination time in the system, which is about a picosecond. Inverse of a picosecond is a terahertz. And so it's this acceleration of charge on picosecond timescales, which then leads to essentially a single cycle pulse of radiation. You can see it's about a picosecond long. So it has all those Fourier content that we're interested in. And then it goes out and propagates through space. And then there's a detection process, which is essentially the inverse of the generation. This technique allows us to do a number of things very well. For one thing, it allows us to measure in the terahertz part of the electromagnetic spectrum. And this is generically difficult to do. The problem is that there's no dearth of terahertz radiation around us. We're all awash in terahertz radiation right now, just from the, if you will, just thermal radiation around us is peaked in the terahertz part of the electromagnetic spectrum. If we're trying to do a measurement, we want to get rid of the blackbody spectrum around us, or say the thermal spectrum around us. And this is a way in order to do that, because we don't measure, let's say, the power that falls on a detector. We're really sensitive to the electric field. And so it's a phase coherent detection that allows us to do very, very sensitive experiments. And it allows us to measure the terahertz part of the electromagnetic spectrum in a fashion that wasn't really previously possible. The other thing it does is it allows us, because we measure in the time domain, when we take the Fourier transform, that Fourier transform is complex. So there's a real part and an imaginary part. And so the thing we ultimately measure is a complex transmission function through the sample. And if we have that complex transmission function, let's say the light is reduced in amplitude after it passes through the system, but it also is phase shifted. We can take the complex transmission function and then we can turn it into, let's say, the complex conductivity. Or if we're looking at a magnetic system, the complex magnetic susceptibility. And being able to measure the complex response directly, this is very, very important. Okay? So example of some particular experiments that have been done. So some that inspired me in my own career when I was a student are those of Joe Orenstein's group, where this is, it's actually the phase stiffness, very similar to the quantity that I just showed you on those thin film of superconductors, but this is for a cuprate superconductor. And again, you can see this is for 2 different samples, and phase stiffness measured not in the few gigahertz range, but measured in the hundreds of gigahertz range. This, again, this dashed line is the Costal condition, and again, you can see this kind of splaying of curves here. And one of the things that this data showed was that there were superconducting correlations which persisted high above the, if you will, the thermodynamic TC in these cuprate superconducting samples, and showing that there were superconducting correlations to high temperatures. Other data coming from my own group, but more recently, perhaps not of great scientific significance, but I think it's kind of beautiful in what it shows. This is the Magneto terahertz response from a topological crystalline insulator system. So a topological crystalline insulator is a kind of topological insulator protected by mirror symmetry. This particular one happens to be doped in the bulk, and so it's really a problem, not so much of topology, but more of kind of a small gap semiconductor system that can be described in terms of massive Dirac fermions. But what we see here is we've taken our superconductor, insulator, topological crystalline insulator, weakly doped, and we put it in a magnetic field. And so there are electronic carriers in the system moving around, and when they're under magnetic field, then they get a Lorentz force, right? So instead of moving in straight lines, now essentially they can undergo circular motion, and we can drive this motion with a periodic electric field of the terahertz that pulse that comes in. And so initially we would have a, say, some kind of Drude-like response, but when you apply a finite magnetic field to it, that Drude response becomes a finite frequency resonance. And one of the very beautiful things that we can do in time-domain terahertz spectroscopy, because we measure the complex transmission function and we get out the complex conductivity, we can, if you will, choose any basis for the conductivity that we like. Now, typically people will choose X and Y bases, right? That's the kind of the simple ones that you typically most, the naive coordinate system that presents to you. But we can also choose right and left, right? So light circulating for right circularized polarized light or left circularly polarized light. These also have conductivities associated with them. And so that's essentially what we've done here is we plotted the dissipative part of the conductivity for left-hand polarized light and right-hand polarized light. And the neat thing about this measurement is that it's actually done in terms of X, and we measure it in terms of X and Y, and then we can just transform to whatever basis we like because we have the whole complex conductivity matrix. And when you do that, life becomes, as we typically know, when you plot things in the right coordinate system, life becomes a lot simpler. And so what you see is this curve here, the purple one, we don't measure in the middle near zero frequency. This is a plot of frequency up to 2 terahertz through 0 to minus here. So we're plotting the left and the right circularly polarized light as negative and positive frequencies. And so the beautiful bit of data that you can see with this is that there is a resonance, the purple curve, that's peaked at 0 frequency and 0 magnetic field. And as you put a magnetic field on it, this whole resonance just shifts off to the right-hand side. That's because it's electron doped. If it was hole doped, the resonance would shift off to the left-hand side. This is the 7 Tesla data here, and there's some kind of details with how all of this was fit. But the thing I want to point out is that it's true for the dissipative part of the response. This is the data we take here. The dashed line is some fit to the data, and is also true for the imaginary part of the response. Again, is also just kind of this continuous curve right through. So this is kind of, if you will, state-of-the-art data, which is made possible by being able to really measure complex response functions just directly from the raw data, without having to do these Kramer-Kronig transforms that I talked about. Let's see, there was something, I thought I had another plot in here I wanted to show you. That comes later on, good. So as another example of the kinds of experiments that are still quite useful, I would say a little bit older, but really is still quite useful, is what's called Fourier transform infrared reflectivity. And what one does in such an experiment is you would come in with light, which is incoherent, so it's not these pulses of light like we were doing in the time-domain terahertz experiment, but it's just, roughly speaking, just a light bulb. It may be visible light, it may be something in the infrared that your eyes themselves can't detect, but the general idea is just the same. Typically the light source for this is really just some thing that gets really, 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 really hot and glows with some particular color, and there's an interferometric experiment that's done, so basically to be able to distinguish one frequency from the other. But at the end of the day, what you do is light comes in, is reflected off the surface of a sample, and goes out and is measured by a detector. We measure, let's say, the power that falls on the detector. Okay? The power that falls on the detector, then we would also then go, after we measure that, we'll go through and we will do something where we take, for instance, gold and evaporate it on the sample and form a mirror. Then look at the sample after gold has been evaporated on it. Look at the ratio between these two things, and that gives us the reflection coefficient. Now, reflection coefficient, that's great, right? It's related to things that we might want to know, like the dielectric constant. The problem is we don't care about the reflection coefficient itself, and this quantity here, you see all these nasty absolute values around, So it's problem, if you will, trying to find out the thing we really want, which is the complex response function. So how do we deal with it? We use our friends, the Kramer-Kronig relations, which I spent some time on in the first lecture. There, I had derived it in terms of the conductivity, but there's lots of Kramer-Kronig relations that can express, different parts of the complex parameterizations of the data. And so one thing that you can do, if you measure the reflection coefficient over a very, very large frequency range, then you go, there's a Kramer-Kronig relation between this amplitude, the natural log of the reflection coefficient, divided by omega prime minus an omega, the integral over infinity, minus infinity to plus infinity, the principal part. This gives you the phase at every particular frequency. And so now you have the reflection coefficient and the phase, and you can use Fresnel equations to figure out, let's say, the complex dielectric constant. Now, this is kind of the standard way of doing optical infrared style experiments. What we're trying to do now with many of these time domain techniques is a way to measure the phase directly. But in these old style experiments, we would have to do it exactly just like this, where even, let's say, if you cared only about milli-electron volt phenomena, you still, in order to do this Kramer-Kronig relation, the limits of this integral are infinity. You can't measure up to infinity, but you need to measure really, really, really high and then extrapolate like heck on the high frequency side to be able to do, say, this integration numerically. And then you can get the phase out. But it introduces all kinds of errors as well as being very, very inelegant. Why the heck do you want to measure 10 electron volts when you're dealing with milli-electron volt phenomena, right? You're off by a factor of 10,000. This is pictures of the inner part. Just I think sometimes it's people like to see what experiments actually look like. This is one of these infrared spectrometers. You can actually buy them, commercial things. For a lot of the other stuff we talk about that there's no commercial instrumentation available, but these infrared spectrometers are commercially available. So that's what data would, for instance, look like. You would measure, this is the reflection curves of a bunch of very simple metals. So gold, silver, aluminum here, right? You know that silver and aluminum are kind of, they look, well, silvery to your eye, right? The reflection curves are essentially flat. They don't have any particular color associated with them, but gold does. So this is the reflection coefficient, and in gold, you can see that it's kind of lower. The reflection at these is high at the lower frequencies, but is less in the kind of blue range, which is why gold looks gold colored to your eye. If you take this data over a very large frequency range, from the lowest frequencies you can to the highest frequencies you can measure, you extrapolate it, you go ahead and you perform Kramer-Kronig relations, you can get the phase out, and from that, then you can go and figure out, let's say, what the complex conductivity is or the complex dielectric function. And so that's what's shown here, for instance, for this is for silver, and this is for gold. And you can immediately see from this data why gold looks different than silver. I mean, it's a bit of a mystery, right? Why should the gold and silver look so different? They have about the same Fermi surface. Their densities are about the same. And the reason is because there's this large extra amount of absorptions for deeper energy levels in gold that end up making this sharp edge here, which we call the plasma frequency, at much lower frequencies. Just as another example of this, this edge here is set by this energy scale in the system, which is what we call the plasma frequency, which has some constants of nature in it, but is also the density of carriers divided by their mass. And so that's why, for instance, it would be weird. It's weird that gold and silver have such different plasma frequencies because they have essentially the same mass and the same density. Why are the plasma frequencies so different? And it has to do with these extra interband absorptions. To give you another example of how optical data in this regard look, this is the temperature dependence of bismuth. Bismuth is a semi-metal. So at high temperatures, there's lots of thermal carriers, so the density is quite large. As you cool down, those carriers start to freeze out, and the plasma frequency gets smaller and smaller. And so that's this edge, if you will, is just kind of moving down as a function of temperature, and that's because the density of carriers are getting small. Another example, this is kind of an older problem now, but I still like it. It's 15 years ago, people were very interested in magnesium diboride. It's kind of the highest temperature conventional superconductor, if you will, at least before the recent discussions of high pressure superconductivity and these kinds of things. So it's about a 40 Kelvin superconductor. And things like the plasma frequency can be very different depending upon what crystalline direction you look at. And magnesium diboride has a feature that it's actually different colors when you look at it with polarized light in different directions. It has to do just with anisotropies of the crystal structure. That's actually what it looks like when you use different kinds of polarized light. And the spectroscopic reflectivity is plotted right there for you as well. Okay, so let's talk a little bit about superconductors. Now, what I had mentioned here, more about superconductors. So I wanted you to think in a very cartoon sense, starting with our friend the Rudabeh model, and as tau gets really, really large, this Lorentzian peak gets very, very narrow, and eventually in some limit becomes a delta function. This imaginary conductivity then moves to lower and lower frequencies and eventually becomes the 1 over omega dependence. We get a delta function and a 1 over omega dependence. That's not the whole story, of course, right? Because if you put enough energy in, we know superconductors are made up of Cooper pairs, and if we put enough energy in, we can break Cooper pairs apart. And so what we might imagine more generically is that a superconductor has a delta function, but then some energy scale, let's call it 2 delta, where delta is what we call the superconducting gap. This energy scale 2 delta is essentially the energy scale to pull or to break Cooper pairs out of the superconducting condensate. Right? So this is in principle something that can be measured. Now it turns out that there's some interesting, this is kind of roughly what you might expect, but it turns out that there's some interesting things that can be done in terms of measuring what we would call the coherence factors. So there are other kinds of condensates that can exist. We can talk about superconductivity, but there's a similar formalism that can be written down, let's say, for weak coupling charge density waves or weak coupling spin density waves. We can also imagine using different kinds of probes to, let's say here we're putting in light to break apart Cooper pairs, but you can also imagine using other kinds of probes and trying to understand making, let's say, quasi-particle scattering, quasi-particle states, or breaking up Cooper pairs in a superconductor. It actually turns out that of all the particular imagined spectroscopies that you could imagine doing, at least of our conventional ones, they fall into 2 classes, whether or not the perturbation in the Hamiltonian with, let's say, bringing in electromagnetic light, or you could imagine doing what we call ultrasound attenuation experiment, which is essentially putting in ultrasonic or high frequency sound onto a particular material and looking to see how it's attenuated in the superconductor. You could imagine doing NMR style experiments. Again, this is kind of an experiment where you're looking to see how, nuclei couple to spin, but in principle, it also is a way to dissipate energy in a superconductor as an excited state nuclei is dumping energy into the electronic system that surrounds it. So in all of these experiments where there's potentially dissipation involved, there is what we call type 1 or case 1 type dissipation, or type 2 or case 2 type dissipation. And we distinguish between these by how does the perturbation Hamiltonian transform under time reversal symmetry. So electromagnetic interactions, because it depends upon the momentum dipole matrix element, it will ultimately, this term, I'm not going to go into the details of it, you can look it up in the lecture notes or in the best book here is probably Tinkam's book. Because it depends on momentum, this piece of this interaction Hamiltonian will change sign under time reversal, okay? Because P goes to minus P. If you're looking at a NMR style experiment, then the thing which is going on in one of those experiments is the nuclei coupling to conduction electrons and essentially flipping spins. Flipping spins, of course, spins change the direction under time reversal. So all of these case 2 cases is where this the interaction Hamiltonian will change sign, and in that particular case, which also applies, let's say, for electromagnetic absorption in S-wave superconductor, you will get this kind of characteristic shaped curve here. If you were dealing with, say, electromagnetic absorption in a weakly coupled spin density wave system, you would get this kind of behavior. Okay, so it's important to separate these. You can see what I plotted on the vertical scale in both here is just generically dissipation in some kind of arbitrary units. And the idea would be that it could be, the plots could be equally valid for a NMR style experiment or electromagnetic absorption or ultrasound attenuation, what have you. Okay? Now, we can also imagine doing one of these experiments as a function of temperature. And they show kind of a notable difference here, whereas in the case 2 case, it's suppressed at the gap edge. In the case 1 case, as a function of frequency, it's enhanced at the gap edge. As a function of temperature, you'll see just the opposite kind of thing, that as a function of temperature, there's a big peak here, just below Tc. Okay, when this was measured, it was one of the first non-trivial kind of, if you will, verifications of the BCS theory of superconductivity, that when they did NMR relaxation experiments on conventional superconductors, this was done in Illinois by Habel and Schlichter in the 1950s, that it was found in the NMR susceptibility experiments that there was a large peak. I've drawn it here as a cartoon, but the real data looks very similar to that, just below Tc. And this was anomalous in the beginning. Why should you get an increase in the dissipation when a system is going superconducting? Right? So it turns out that this falls out of the BCS formalism very, very nicely, and this prediction of a peak that now we call generically in such experiments a Habel-Schlichter style peak, first done in the context of NMR, but is generically seen in many different kinds of experiments. Can be seen in D-wave superconductors, in neutron scattering and finite momentum transfer, or in conventional superconductors. Can be seen in a cavity-style experiment like I told you about earlier. So this is in superconducting niobium done by cavity perturbation. And one of the interesting things is that this actually experiment in microwaves was actually done incredibly late. It was Habel-Schlichter peak was first shown in microwaves in 1995. Nobody had ever done the experiment before that as a function of temperature here. So this is the real part, shows a peak just below Tc, and then the imaginary part kind of grows in this fashion like an order parameter. Okay, much earlier, I don't have the date on this, unfortunately. I think that this particular data is 1962. This is transmission through lead films, and you can see this kind of characteristic suppression at the gap edge. The curves here, this is the theoretical curve, and these kinds of enhancements at low frequencies, that's the peak that you get in the consequence of, like, say, a Habel-Schlichter peak, if you're doing very, very low frequency microwave style experiments. Okay. So in a more modern context, this is work by my group on highly disordered niobium nitride. So niobium nitride is a material which is a superconductor, but you can make it very, very disordered and push it right up to the insulating edge of the metal insulator transition. And so this is something we were interested in these systems, was how does superconductivity behave in a system which is really just on the verge of localizing. You put enough disorder into a system, it can localize. And so there's a bunch of details with this, but really just what I want to point out is this is the optical conductivity as a function of frequency, and you can see that there's this kind of distinct threshold here. As we're making the system higher and higher disorder values, let's say this is lowish disorder, higher disorder, this is the disorder is getting larger and larger. And as the disorder gets larger, the conductivity is getting smaller, and at the same time, Tc is getting smaller. This kind of threshold goes down. And then there starts to be a very non-trivial behavior right near the localization transition, but that's a different story, or a different, let's say, more extended talk. Let me skip that. I talked about Habel-Schlichter peak. This is this peak just below Tc. One should be careful because the annals of superconductivity are full of people seeing particular peaks and misinterpreting them. And in this is on YBCO, so it's a high temperature superconductor. You see a bunch of peaks, none of which are Habel-Schlichter peaks. So there's a sharp peak, this is where Tc is. This peak here, that's right around Tc, it's actually, if you look very, very closely, it's actually mostly above Tc. And this one has to do with actually superconducting fluctuations. So the same kind of fluctuations that we saw in the two-dimensional superconductor that was emblematic of this Costal-Brzezinski transition, here are seen in YBCO in kind of a system in YBCO, which is kind of on the boundary of being quasi-2D or 3D. Still superconducting fluctuations, not of the Costal-Salis variety. This huge whopping peaks down at low temperatures, this has to do with the D-wave superconductivity found in the cuprates. So because there are certain places in momentum space where the gap disappears, there are low-energy quasi-particles that are there, and these low-energy quasi-particles themselves, even though the system is superconducting, at finite frequency, those quasi-particles can dissipate energy, and they form these very, very large peaks here. This is a D-wave superconductor, And it was early evidence for it not being S-wave, YBCO, that it had no Hebel-Schlichter style peak. The nature of the coherence factors are different in this system, so that it doesn't show that, but it still shows these peaks. Okay, let me talk a little bit about sum rules. Okay, so sum rules are something which come from the the Kramer-Kronig treatments of response functions, and are something which is super useful. So I wrote the Kramer-Kronig relations earlier in terms of the conductivity, but there are also Kramer-Kronig relations for the dielectric constant. And so we can write the Kramer-Kronig relations for the dielectric constant in this fashion here. And to save a little bit of math, I'm just going to break it up immediately into two pieces, or a little bit of writing. I'm going to break it up immediately into two pieces, and then let me come back and explain what I've done. Okay. Okay, so this is, Kramer's Kronig relation, right, relates an integral over all frequencies of one part of the response function to the other part of the response function, say the imaginary part epsilon 2 to the real part epsilon 1, and it's an integral over all frequencies, but here I've broken it up into two pieces, okay? So here, I'm going to consider that there is some frequency scale, omega c, which is a frequency which is above all possible transitions. Okay? Okay, above all transitions. Let's say Q equals 0. So if I make some particular solid and I have low energy, I have energy levels right near the Fermi energy, and I can excite those with milli-eV or 1 eV energies. I have orbitals which are lower down, and I can pull those up, et cetera, but eventually, if I go to high enough frequencies, I've essentially exhausted all possible electronic transitions, and I would expect for omega much, much greater than omega c, that epsilon 2 is equals to 0. Okay? So I expect some frequency high enough where there's no more dissipative response of the system, some very, very high frequency. Okay? In which case, then, if this frequency is high enough, then this term here, right, is 0 by construction. Okay, good. So the second integral is 0. The first integral is no, let me do it over there. Okay, so in the first one, we are going to imagine, since we're talking about omega much, much bigger than omega c, then I can take it and I can write it as epsilon 1 equals, as a function of omega, minus 1, then I can write it as 2 over pi omega squared, 0 to omega c, omega prime, epsilon 2 as a function of omega prime d omega prime, right? And I've been able to do this because I'm talking about omega so much, much bigger than omega c that the omega prime in the numerator over here just drops away. Okay? Now, at high enough frequencies, I put all of my atoms and I've made a solid, and at low energies, they kind of feel the lattice potentials, if you will, and they very much know that they live in a solid. But high enough frequencies, you can think of it classically, that if I'm taking at high enough frequencies and I'm going ahead and I'm jiggling these electrons, they can, if you will, make classical excursions that are very, very much smaller than an atomic distance. And at high enough frequencies, I would expect that none of the lattice physics is really relevant. And at high enough frequencies, all the charges in the system behave ultimately like free electrons. Okay? So for free electrons as omega goes to infinity, I can assume then that the dielectric constant of this thing as omega goes to infinity, the free electron result at high frequencies is 1 minus omega p squared over omega squared, okay? Where omega p squared is just, again, always my NE squared over m, which is the so-called plasma frequency, okay? Good, now, so let's see, actually, let me just, nope, I'm not gonna be able to see it, honestly. All right, so I have 1 minus omega p squared over omega squared equals 1 minus 2 over pi omega squared integral of omega prime epsilon 2 omega prime d omega prime. Okay, good. I just cancel everything that I can, right? The 1 in front, the omega squared here, the omega squared there, and ultimately what I get out of this in the end is that I get 0 to omega c is omega epsilon 2 omega prime d omega prime equals pi over 2 omega p squared, right? So what this says is that there's an integral on the dissipative part of the dielectric response, if you will, a first moment sum rule, which says that with some constants it's related to the plasma frequency squared, where the plasma frequency squared is, I wrote it down over there, which is the density of carriers divided by their mass. Okay? Now, this is an integral which is going up to omega c. So we have to be a little bit careful with what we do when we're interpreting this in this fashion. And so ultimately, you know, if we've defined this as omega c is some energy scale where there's no more absorption in the system, then it doesn't matter at that point. I can just let omega c go to infinity, and then the density of carriers will be just, it encompasses all the possible spectral weight, and I will expect that the n in this expression for the plasma frequency is just the density of carriers. But I can also imagine situations where I let omega c, let's say, imagine I have some kind of low energy bands which have, let's say, a bandwidth of a few electron volts. Then I could imagine that this omega c is just this integral, let's say, over the bandwidth, or a few times this bandwidth. Or some other carriers, you know, let's imagine that I have bands which are 100 electron volts down, right? So I can imagine some kind of situation where I look to see, you know, what this expression is as I change omega c. And I kind of bring in different manifolds of bands. So there's a beautiful experiment that was done on aluminum now 40 years ago, 1978. And so what I want you to look at here first, there's a few curves here and I'll come to them in a moment, but the first thing I want you to look at is this one here, which is the number of effective carriers versus energy in units of electron volt. Here, this is a plot of basically looking at this sum rule, which I've just derived for you, as a function of the cutoff. So the integral to infinity is all the charge carriers in the system, but this energy scale here is now as a function of changing this cutoff of the integral. And so what you can see is that, you know, so this is at 0.1 electron volt, 1 electron volt, 10 electron volts. And so the energy scale comes up. How many valence electrons does aluminum have? 3, right? And so you come in here, you go to something of order 10 electron volts, which is the bandwidth of aluminum, and you get 3 electrons. This is with this expression with the free electron mass of aluminum. So then you keep going and you hit the L, you hit the, I'll come back to this point in a moment, you hit the L edge, which is an X-ray absorption energy of aluminum, and the number of carriers comes up. The K edge is even farther down, coming all the way up. What's the total atomic number of aluminum? 13, right? So you can do this optical absorption experiment and measure the number of electrons per lattice site in aluminum. Now, this is the first moment sum rule for the imaginary part of the dielectric function, but there are other sum rules that can also be derived, and I'm not going to go through those, but they're done essentially in the same way. There is the quantity of the imaginary part of 1 over epsilon, the dielectric constant, is a function called the loss function. And there's a first moment sum rule on the loss function. You can see it equals the same thing, modulo a minus sign. Kappa here, kappa is the absorption coefficient of how does electromagnetic radiation be attenuated as it passes through material. And there's another sum rule. There's a whole host of other sum rules. There's sum rules on the index of refraction. You know, we use these things a lot, and they're beautiful because if you have no idea what you're doing, as we may in a correlated electron system, you can always use sum rules in kinds of ways of trying to understand your data, or at the very least just trying to say something clever about it. One of the interesting things about it as well is you can see that, you know, these various energy scales, let's say the L edge, the K edge, what have you, they are always apparent in the data, but the rate in which you asymptotically approach these densities, right, differs on the particular sum rule that you might want to look at. For instance, the loss function is a function which is peaked near the plasma frequency, and so this energy scale here, where this guy goes shooting up, this is the plasma frequency of aluminum, right, which I'd shown you in one of those previous plots, is about 14 electron volts. Okay, so what's the moral of the story? The moral of the story is not aluminum. The moral of the story is that you can use sum rules for extracting out different, if you will, by moving the integration constant and be able to understand different things about the physics on different energy scales. This is exactly how this plot that I showed you early on was made. Right, so if I know the density of carriers, where's my plasma frequency? Oh, did I already erase it? Okay, there's the plasma, anyway, there it is right there. Plasma frequency. So if I know the density of carriers, I can do a restricted sum rule and find out what is the effective mass of the system up to some particular energy scale. Again, as I have a sliding scale on the upper limit of this interval. And so if I know that my heavy fermion physics is all found at some kind of low energy scales, low frequencies and low temperatures, and I look at some restricted sum rule on that energy scale there, then I won't have very much spectral weight, right? So if I don't integrate up very high, and I know the density of carriers, and I don't have much spectral weight, then the mass is large, right? So this suppressed spectral weight corresponds with large mass, and that's exactly how this plot was made. Okay? So they observe some kind of low frequency Drude and integrate over it and get the spectral weight out. So another consequence of, or another example of using sum rules is work that was done in my group on topological insulators. So we did here, these are optical conductivity experiments done with time-domain Terahertz spectroscopy on a thin film of a topological insulator. So topological insulators, these are of course related to what Gil was talking about in terms of topological systems. I'm going to talk in depth about them tomorrow, but for now we want to think of them as materials which are bulk insulators, but are wrapped on all sides by conducting surface states. And we're going to talk a little bit about the magnetoelectric response of these systems, but for now I want you to think about the surfaces as kind of metallic conductors that can undergo some kind of quasi-classical dynamics where charges can move around with, that could be described by something like a Boltzmann transport equation or Drude transport equation. So this is a plot of the optical conductance as a function of frequency in the terahertz part of the electromagnetic spectrum. The red part is the real part of the conductance, the blue part is the imaginary part. This big peak here at 1.9 terahertz, that's a phonon. So a lot is known about the phonons in bismuth selenide because before it was a topological insulator, bismuth selenide was a magnetoelectric material. Sorry, a thermoelectric material. It was a thermoelectric material. It's still a thermoelectric material. If you go to, buy, not that I have one of these, but if you would go to the airport and you buy like one of these executive wine coolers that will, when you go to work on Wall Street for your $500,000 a year job, and you have in your corner office your executive wine cooler keeping your champagne cold, that'll have topological insulator material in it working as a thermoelectric. There it's probably bismuth telluride. But the point is not that. The point is that a lot is known about the phonons, and this phonon is called the alpha mode in the old thermoelectrics literature on bismuth selenide. So what we're particularly interested in is this peak here, which is peaked at 0 frequency and has about a width about a terahertz wide. Okay? There's a real part and an imaginary part, and we can take this data and we can fit it with our Drude model, our Drude-Lorentz model, if you will. You can see that the phonon is well fit by some kind of Drude-Lorentz line shape. There's a real part and imaginary part, and everything fits beautifully. We can take that data, and that was data of a particular thickness of 60, it was a film grown of 64 unit cells high, 64 nanometers. So it's bismuth selenide, it grows in this kind of layered structure. And so we call it a quintuple layer because there's 5 atoms in the unit cell, and it goes in this 5-atom block. So here is the real conductance plotted as a function of frequency. This curve here in red is the data I was just showing you, okay? But these are different films of different thicknesses. Now, what you can see is we're going to take this data, and we took it, we fit it to Drude-Lorentz, and we extracted out the areas of these various features, okay? Now, the phonon is a bulk feature of the material, right? It's associated with the mutual motion of bismuth and selenium atoms kind of rocking back and forth with respect to each other. And so if I make the material twice as thick, I expect it'll absorb, roughly speaking, twice as much energy at that frequency. What I want to convince you from this is that the low frequency stuff is entirely coming from the surface states. Okay? So this is the sum rule of the optical conductivity. Now, if I'm talking about massless Dirac fermions on the surface, this relation in terms of band mass, et cetera, it's a little bit different, but the essential point is still true. There's still a sum rule, of which the details of which I don't want to get into now, but there's still a sum rule for the optical absorption on the surface, okay, of massless Dirac fermions. Okay? There's also a sum rule that's associated with the phonons as well. So this is a plot of the real conductance versus frequency. There are some changes here in the low frequency spectrum. This is a plot of this area of the curve of the phonon versus the Drude part here as a function of thickness. Okay, so it's basically I'm taking the area out and I'm appealing to the sum rule, and what you see is that the phonon is linearly proportional to thickness. This makes sense, right? It's a bulk feature. I make a material twice as thick. It absorbs twice as much as that frequency. This sum rule allows us, if you will, to write down some kind of absorptive strength of the material. But the low frequency Drude is independent of thickness. We make it twice as thick. It doesn't absorb anymore. I mean, there are some changes here in the low frequency spectrum, but those changes are such as to preserve the area of these features. Okay? And so really it's the sum rule which allows us to do this. And this, what this allowed us to do was to show essentially in these samples perfect, essentially complete surface transport in this 2D thin films. And I'm going to come back and talk about this more tomorrow. Okay, now what else can we do with these systems? So I've talked a lot about this, overly simple Drude model. We can make the Drude model a little bit better by talking about writing down a slightly different, an extension of it, and I alluded to this before, of what one might call the extended Drude model. So if I go and I write down the quantity, let's call it m star as a function of omega, and the imaginary part of 1 over sigma, and the real part of 1 over sigma. So sigma is again a complex quantity, but the quantities that I want to consider here are not the 1 over the imaginary part of sigma. I want to consider the imaginary part of 1 over sigma, right? Not 1 over imaginary sigma. Imaginary sigma is just sigma 2. This is the imaginary part of 1 over sigma, and this is the real part of 1 over sigma. And if you go ahead and you would do this just on the simple old Drude model, when you go through this direction, you'll find that for the top quantity here, you'll just get 1 out, right? It's a ratio of a mass to a mass. It's just here, it's just the ratio to the band mass of the system. And here you'll find that you get, for this expression, you'll just get 1 over tau, the scattering rate. But writing it in this fashion here allows, so if sigma is derived completely by the Drude model, that's what you'll get out. But real systems have other effects that are in them, such that the line shapes aren't these perfect Lorentzians. And those deviations from things being perfect Lorentzians encode other kinds of more subtle physics that we may be interested in. Okay? And so that's essentially what's done here. And 1 over tau allows you to think about a frequency-dependent scattering rate. So if I imagine a 0 frequency excitation of the system, there's not very much it can interact with, right? As it moves along at something infinitesimally close to 0, it can bump into static disorder, but it can't excite any real excitations of the system. Imagine, say, an electron moving along, and it cannot interact, let's say, not in terms of scattering off and making a real excitation, it cannot make an optical phonon. Imagine if I have an optical phonon of 20 millielectron volts. If I inject 1 millielectron volt into the system, it doesn't have enough to create an optical phonon. But imagine I excite an electron-hole pair with 21 millielectron volts. Now that electron-hole pair has a new route to decay, it can create an optical phonon of 20 millielectron volts and still have 1 millielectron volt left over for itself. Okay? So the point is that this scattering rate can be strongly frequency dependent, and this is what is done, if you will, as a first step for understanding interaction effects in systems. Okay, so that's what's done here on some very simple systems. This is copper, 1 over tau, and that's gold of 1 over tau. Simple metals, we believe these things are Fermi liquids. And the scattering rate, the frequency-dependent part in those systems, the Fermi liquid-like scattering is that the scattering rate should go like omega squared. And you can see that, well, the data has some noise in it, but essentially it's consistent with the omega squared dependence. Okay? If the imaginary part of 1 over sigma and the real part of 1 over sigma, these also have a Kramer's-Kronig relation that relates them. So if I know the imaginary part of 1 over sigma over all frequencies, I can get out the real part of 1 over sigma at all frequencies. And that means if I have non-trivial frequency structure in, let's say, the scattering rate as a function of frequency, I also then have non-trivial frequency structure in the mass as a function of frequency. And so that's what you can actually see here. This is 1 plus lambda, and I'm sorry, I didn't define that properly. This is defined here as just that lambda is like kind of a mass renormalization factor. So if mass is not renormalized, lambda is 0. And so you can see there's this kind of characteristic frequency structure here, which is quite emblematic for these kinds of renormalization effects. And this is the copper one, and silver and gold, and there's copper being 3D has slight mass enhancements that are not seen in the silver and gold effects there. This is not, let's say, that dramatic in the case of these noble metals, but we can look at these heavy fermion systems again, and then you can see all kinds of interesting effects. Again, this fits in a little bit with what I was telling you earlier about sum rules, and in fact, you need to consider sum rules as kind of part of this whole formalism looking at extended Drude models. Right, so this is a plot here. This is another heavy fermion system, cerium aluminum 3, and this shows the scattering rate as a function of frequency on the top, and this is the effective mass as a function of frequency. And so the low frequency limit of this, these are going to be these kinds of things that we could, if you will, infer out of the sum rule, but here it's kind of directly coming spectroscopically out of the measurement itself. And you can see in this system here that as this is higher temperatures, this is lower temperatures, and as you are at lower temperatures and you increase your frequency, the scattering rate increases, and this is basically coming from the fact that you can couple to various kinds of inelastic scattering processes in the system, the very same processes that increase your effective mass, in this case, can make it of order about 400 for electron masses, or 400 band masses in this case. This is data. The other data was from another group. This is more data back to my group. This is data that I showed you earlier, but now you have more theoretical machinery to understand it. So this is the effective mass as a function of frequency, and this is the scattering rate as a function of frequency. So you can see there's this kind of turn on in the scattering rate as a function of frequency at the low temperature limit, and it's essentially independent of frequency at higher temperatures here. This is some model for something. I think I'll just skip that. This is very nice data. This is from Tom Timmis' group from some years ago, doing extended Rudabeh model analysis of Bismuth 2212, which is a two-plane cuprate superconductor. And what you can see, again, are these very kinds of characteristic shapes. At high temperatures, the scattering rate is approximately linear in frequency, which is a very characteristic form of the strange metal state in the cuprate superconductors. But as you cool down to low temperatures, there's this very pronounced kind of almost gap-like phenomena that in some places has been called signatures of the pseudo gap effect. And what this comes from is still, after all these years, a matter of some great debate. I don't want to get into the details of it, but I just want to point out the general use of this kind of technique of categorizing, if you will, not categorizing, but analyzing various energy scales in various physical systems. And here in the cuprates, which is this very strongly interacting system, again, you can see this kind of increase and then this kind of cusp-like shape as well. These are not written in terms of scattering rates. That's a scattering rate. But they've actually been written here in terms of optical self-energies. So if you're familiar with the notion of a self-energy from, let's say, the theory of a Fermi liquid, these could be related as analogous quantities, not as the quasi-particle self-energy, but as optical self-energies, which are a related quantity. So I have, how long left? About?
A little bit more than 5 minutes.
A little bit more than 5 minutes, okay. So I want to say a few final things about nonlinear optics and its use of symmetries, and then say some things also about topology and Berry's phases. And I'm going to talk more about topology tomorrow in the context of the topological insulators. So everything I've talked about today is at the limit of equilibrium systems and linear response. And that's not an accident. There's a, I had thought for a long time that, I was interested, initially I was working on things like cuprate superconductors. And these are very, very complicated systems. Let's say some correlated system, which is, roughly speaking, let's say, impossible to understand. There was a huge amount of work that had been done for many years where people were using high power lasers to investigate these kinds of correlated systems. So if you're using that kind of high power laser, you're pushing a system very much into the non-equilibrium regime. And so non-equilibrium physics is also, let's say, impossible to understand. So if you take a correlated system like a cuprate superconductor, which is impossible to understand, and non-equilibrium physics, which is impossible to understand, and you put them together, simplicity is not the natural outcome of this. So for many years, I was really opposed to doing anything with non-equilibrium, non-linear responses of systems, because I just thought if we can't understand the linear response, then there's just no hope. And the linear equilibrium response, there's just no hope of making any sense of it. I kind of changed my tune on this a little bit, and that's for a variety of reasons. One, because I think that there's lots of interesting things to be done in terms of the non-equilibrium situations, but with topological degrees of freedom. And we heard in Gil's talk this morning, this is what this was about. There was an assumption that the free fermion perspective was a good one, which it probably is. And then from there, kind of figuring out all the interesting non-trivial physics that comes on top of it. But it also turns out that nonlinear effects of solids can give you all kinds of information in a reasonably model-independent way that I think we're really just starting to see the beginning of. And it's now the development of various kinds of sources that I think nonlinear, non-equilibrium effects of solids, these kinds of responses can be more systematized, where I think we can start to make some sense of what's going on. In the interest of time, I'm not going to, well, I will just say a few things very, very briefly. So if you're interested in, the fact of the matter is that nonlinear responses of solids allow you to say various things about the symmetries of systems. This also occurs at the level of linear response. And so one of the ways that we like to think about linear responsive systems is in terms of these 2x2 matrices that that are called in the optics world called Jones matrices. And so if I think of a polarized light beam, a coherent beam, which can in principle have polarizations in the x and the y directions, like that, incident is I, and outgoing is O. There's a 2x2 matrix which relates this vector into an outgoing vector. Now, this is a rather simple situation of some 2x2 matrix. It turns out that we're going to consider the symmetries of the material. So the material has some kind of, if you will, point group symmetries. It has the possibility of inversion symmetry. It can have reflection symmetries. It can have mirror symmetries in the plane, out of the plane, mirror symmetries in various directions. We're talking about discrete symmetries in general. It can have time reversal symmetry. And it turns out that this very, very simple matrix, which is just relevant at the level of linear response, has all kinds of constraints. Those point group symmetries create an algebra which relates these coefficients to each other. And so if we know something, we can, if you will, measure all of the complex components of the Jones matrix. We can tell something about mirror symmetry breaking in the system, or time reversal symmetry breaking in the system. We can do a variety of different experiments in that fashion. So it doesn't look like there's much there. This is actually, if you're interested in all these details, this is worked out in this particular paper of mine. The thing that I wanted to say here is that although there's lots of information in this 2x2 matrix about symmetries in the material, if we start talking about the nonlinear response of the material, this is governed by a higher rank tensor, which has even more information in it, right? And so, right, the general point being that if I'm talking about, let's say, the polarization created by an incoming electric field, I will generally write it, as I did in one of the very first slides, as a second-rank tensor, which is the polarization susceptibility in terms of an incoming electric field. But this is just the first term, and I can imagine all kinds of other terms here as I start I, J, K, EJ, EK, I, J, K, L, EJ, EK, EL, etc. Right? These guys here, this has some amount of information in it in this susceptibility tensor, very similar to the transmission tensor that I just showed you. We called that, in the linear case, the Jones matrix. These susceptibilities, though, you can see they're governed by these higher rank tensors, and they have a lot more information in them about symmetries. So this has been used quite a bit recently to look at subtle symmetry breakings in systems. And I think this is one thing that is really just at the very beginning. The best work in this regard has been done by Dave Shea's group at Caltech. I was fortunate to be involved with one of these experiments where we found a subtle symmetry breaking that occurred at the pseudogap temperature in YBCO. So one of the things that people have been discussing for many, many years is whether or not the pseudogap in the cuprate superconductors is indicative of some kind of crossover phenomena from one high temperature state to some other phenomena at lower temperature, but where there wasn't a distinct phase transition? Or was there a really true line of true phase transitions which are characterized by a new state of matter, a new phase which has distinct broken symmetries? And so one of the things that we could show, which wasn't seen by any other experiment previously, is that there are some symmetries which are broken at the pseudogap temperature. And it really is kind of a, I think these are subtle symmetry. These are, say, subtle distortions which didn't appear in other techniques, but these nonlinear techniques are a way of seeing it. And Dave has done some very, very nice work also on iridates, finding kind of similar effects. And this is, again, kinds of things that hadn't been seen in more conventional probes of symmetry. What happened in the case of iridates is they found subtle consequences of these symmetry breakings, and then the X-ray diffraction guys and the neutron diffraction guys went back and looked, and they could find that they were there. I think I'm basically out of time. I wanted to say some more things about Berry's phases and topology, but this actually fits into my lecture tomorrow, and so maybe I'll just postpone it until then if it's time to stop for now. And so anyway, thank you for your attention. I'll take questions if there are any. Okay, good. You're all exhausted.
See everyone tomorrow.
Thanks for your lecture too.
Did Kristen get back to you?
Version symmetry for transition, which happens to describe not the real case. Whether the symmetry of the system second harmonic response not stock. So it uses whether that happens for important reason or happens for unimportant
一个是讲的欧拉类的那个满足多样式，但他讲了一个，他讲的这两个欧拉类双那个满足多样式，那就看别的书。
你让我再刷一本 GT，
那看别的书。
啊 ，GT 不太难刷了 ，GT 做的简直是。
对，我在问那个 frequency mechanism measuring insulator 的区别，那个是跟1和2那个范围的给老板们买。
Yeah. We've got good spins, which are the ones that want to generate.
But what if you,
再到处开做3
you also mentioned that in the Hamiltonian there is no term source 1 into omega over 2.
这相当于在
If I just put in like a percentage like external wave of frequency of omega over 2, does it mean that you can just mix those two high or
If you have this thing as a background noise, that will disperse and give some coupling. So it's not, so that thing is not restricted from. That said, actually the This humanity is level and some dark state. This was what you referred to, right? The things but then that requires like going like with some paths in photon space that will give you.
I'm John from MIT.
Oh, hi. Nice to meet you. How are you?
That will give you the combination that will give the resonance.
Your talk reminds me of a work I did with Patrick, and it's about optical conductivity from a pair density wave.
Repair density. Okay.
Yeah, so it has a different coherence factor. So the optical conductivity looks just some kind of like an SDW case.
I see.
Yeah, so it's very different from their momentum pairing.
Yeah, I see. Okay.
Yeah, and its peak is proportional to like the pairing momentum square. And it's very.
So there's some factor which has to do with basically the state itself, which comes in, which flips sign. Well, pairing momentum squared. So why does it? So usually we think you get these case 1 factors if the interaction parameter
In this case, it's
changes sign under time reversal. So why does that happen here?
You don't want to go away from this line at all. But in order to stay.
So in normal case for a superconductor, P goes to minus P.
Quasi-crystal.
Oh, I see what you're saying. It's squared. That's what you just said. Got it. Yeah,
potential.
I see.
Yeah.
If you just look at it straight.
So and it's very anisotropic. If you have pairing in one, yeah, one direction, and it's maybe usually in the Terahertz region.
So this would be this is a prediction for something on set, the pseudo gap temperature. Is that right? Pair density.
In effect,
if it's
you have
in
some,
cuprates.
so suppose you calculated your
And some other materials may be the
the same way that we calculate by just making like
material.
a resonance with
So,
single photons.
I remember there's a candidate
from this point to that point.
in 2014.
They
They found like a
another bulk
candidate
state over
of high density
here.
wave.
If you take
in
so many
yeah,
photons
in
of omega 1
susceptibility measurement, but
there's another state here
they
in the
cannot
bulk.
confirm it's a
But you
high
should
density wave only from this
resonate with
susceptibility.
each other.
And we suggest them
higher
doing
order,
this optical,
Mhm.
yeah, but they cannot do Terahertz.
But because this is weak drive.
The Terahertz experiments are hard to do unless you can do a transmission experiment.
Actually,
And then generally you need a thin film.
From here to here is
So for these organics,
exponentially.
they're typically some small crystals, and so they're hard to
So,
look at very good.
So that's the
low
argument
frequencies
why they
because,
can actually
You know,
survive.
at low frequencies,
Make that
anything which
I
conducts
showed in the
has
end.
100%
I didn't
reflection.
completely explain it, so I'm sorry.
So you
So
know
what
your
see here
signal
is
is
the
like
result of
if you have
driving
density
the
wave,
system
if you
with,
put it in
two
terms of
frequencies.
reflection,
So you have
it probably
this
goes from
analogy
being
with superconducting proximity, you have
99.9%
three
reflection
superconductors,
to
one is
99.98%
grounded, the other is
reflecting.
V1,
And so it's a very, very hard experiment to do. You know, because in other words, anything which is a good conductor is 100% reflecting. And so you're trying to differentiate different kinds of good conductors.
And golden mean
And
is like
what it means then is that the reflection is almost 100%. And you really have to do a very, very accurate experiment at low frequencies, which is hard.
The wave function.
Is that because of the 1 over omega
So-called
imagining?
normal, so the wave
Well,
function is
I mean,
like
not
modes
even
that are
necessarily
edge
just something which is a conductor at all.
Mm-hmm.
If something has
this
a
is zero
real
frequency, you see a
conductivity
nice localization
in the limit of zero
So the only
frequency,
thing is that we cannot distinguish.
you know, so in other words, what I just mean is like, one.
So this is near the zero frequency.
This is the reflection.
This is
So if something
the half frequency. Sorry,
zero frequency
omega equals 1, and this is omega equals
is not equal to, if it's not equal to 0,
You see, they also
the reflection is
near
1
the edges.
at 0.
They're at the same place.
And
But
so
they're very distinct, right? They don't melt into the bulk. Like the
You
bulk
have this,
contribution is very small. And it's like finite size.
very tiny change that you can have, you know,
So definitely
some
K
tiny little
exponential
amounts of structure here, which,
what
this is the plasma
is
frequency, so
just
this
saying,
is,
let's just
you
look
know, if it's a
at the
cuprate, let's
Majorana
say,
operator on the
this is
edge.
half an electron.
Without bias, without
What's
any-
this here? I don't know.
any
It's,
prejudice. We just
200.
C plus C dagger on the first
yeah,
side.
point, yeah, it's like
And then
200
calculate
million.
the correlations between that
And then you have your pair density
and
wave, which
itself
has
at a later
structures
time,
on
starting with some
order
generic
of
state, like half
10 millieV or something, you know, like something of
so it's not
order
started
is
at any particular
transition
state.
temperature.
It's noisy,
Yes,
because
right? You
you're
said
not in a
terahertz,
particular
right?
state.
Did you say terahertz?
But then you do a
Yeah,
Fourier
for
transform,
the others.
and you see the
Yeah,
terahertz
for the other
a
sample,
large peak
right?
at
So
0,
then
a
it's,
large peak
we're
at
talking
half,
terahertz.
which is half of omega 1,
So
and
it's
a large
like
peak at
4 million.
half of the golden mean.
Yeah, so it's like,
Yeah,
what-
exactly. So these are
you gotta
just
take this
saying
thing
we have
and
those
blow it up.
states
And it's, you're looking at the tiny,
available
tiny
on those
difference from
frequencies, and
1.
they're definitely there.
And so it's
And if
super
you
hard
add
to
noise
experiment.
to the Hamiltonian,
Would it be better if
then
it's a
this,
superconductor?
peaks
so
just
it's become a
broaden
conductor?
out a little bit.
Well, but this is reflectivity.
Of course,
Well,
probably
this is
Right,
the
so
energy
it's,
is no longer
it's,
protected.
so the good, so this is why, superconductors are very hard to do. Like if I look at lead, when it goes
But the
superconducting,
states are still there.
it hardly changes at all if I look at the reflection. Because it's a
My
good,
impression would be if
so
you
it's
instead
it's a
of
good,
like
it's a
having
good metal, and
operator
its
over
reflection
two,
is 1.
you have just 1
And then it
over
becomes a
2 here.
superconductor, and
If you
it's
have
like
instead
a
of what? Say it again?
super good,
Instead you have
you know,
like
it's
a
even closer to 1.
0.8, like golden ratio.
You know what I mean? Is that it's
have like
almost 1, and then
1/2
it becomes even closer to 1.
Yeah,
So
so
it
you
goes
have 1/2
from lead,
right?
We'll have
onto
at 1.
reflection
Yeah, then you
experiment.
can
Low frequencies.
emphasize it's only
It's
You get rid of even like the
99.99%
zero.
reflecting
yeah,
every
everything
normal
else.
state.
no.
And then you get, you know,
so
it
when
goes
you do
from
that,
99.9% reflecting,
and 1, right?
and then, you know,
so the period,
that's
so
what it
1
does
is
to
like
the
a resonance
superconducting
of the half.
Right.
So it's very,
If
you
I
gotta
can do
tell the
another
difference
folding,
between
so you have
99.9
like,
and 90.999. You know, so it's very, very hard to experiment to do.
I see.
If you can do a transmission experiment on a thin film, that's how Tinkham did those experiments. Then, years ago, and that's how we work on
With
superconductors
1,
now.
you do a
If you
folding,
have a thin
right?
film, then
one
you can
here
do a
and then
transmission
start
experiment
copying,
through it.
With the
And
half,
then you can maybe see
you
some
do another
differences.
folding. Now,
But when you're
if you
doing a
have a
reflection
half,
experiment,
then you
then
bring the
on a
omega
fixed
over
sample,
2,
then the reflection
and
is
copy
almost
it
1.
by omega
It's
over
very,
2,
very
right?
hard to see it.
So it goes back to 0.
Yeah.
And then,
So,
so then we can have phases.
But, you know, if
Am
people
I
could
wrong
make
on
a
that,
thin
you know?
film of this organic,
But those would
then
be
it would be
phases
very
that
nice
correspond to the phases before that
Because
have
nobody's making
either a
those.
0 Majorana or a pi Majorana.
Right. So does it mean that the
So you're back
should be
with
destroyed?
Patrick Lee?
Yes.
It could be
But,
hybridized with the pi
yes,
mode. So
can
if you
have
had just the 0 mode, but
Yep.
without the pi
Yeah.
mode, then nothing would happen.
Maybe it's something to do there, with that, yeah.
Depending on what
The problem with cuprates is that there's so many,
It's either Majorana or omega
so you
over
do,
4.
let's see, your prediction says that there should be,
But it's true. So as soon as you provide omega over 2,
Maybe at the pseudo
protection
Then,
is
there is
but
some
then
extra
the other picture where you have this shifted, like
I'll keep looking.
in the
for it.
commensurated case,
Yeah,
you have a
so,
shifted
there's
box
all
state,
these complicated
and all
things
the
that happen.
majorities were just
Yeah.
merged into the box states. Does it
problem.
apply here in this case?
So this was not a commensurate case. This was just saying this
So
will
how
happen.
many times
generic-
is organic? See what they have these
this
horrible
will happen
chemical
generically.
formulas. The organics are somehow
This is in a
simpler.
picture, right?
In a
This
one
generically
over-
happens.
In a 1/2 case, this will happen.
But
Uh,
anyway, so you have this
there's
recent
no-
paper.
so one
I mean,
over
I
two
know
is,
about
uh,
this crystal thing.
it's,
you can read that.
Right. So 1/2 is immediately
1 or 2 years.
it's like with one photon. Yes. Yeah, and exactly right. So it,
Yeah.
if you have commensurate, so not one.
Yeah.
I don't know.
Yeah, Z die.
I can't
That's
remember
already
my
the whole thing.
primes past 100,
Yeah,
but
versus
I don't
Z.
know, like 31 over 17 or something.
Very large.
It's a very large commensurate number, but
Would your
very
guy
commensurate.
have a
Sorry,
Hall
two
response
large
in the
integers. The numerator and
conductivity
denominator.
tensor? Like it has off-diagonal term,
And,
but the diagonal term can be very small, like a superconductor.
Yeah, so that would be like the
Do I
finite size
detect the
effect.
polarization
Because the quasi-periodic
change
potential
of the
would just
light,
become periodic
or-
with some large
Yeah.
periodicity.
Yeah,
You
so
still
you
have, like,
detect,
exponential
you need
Yeah,
to-
so you have exponential decay.
So
a little
what's the
bit,
question
and then
about
it
whether or
picks
not,
up.
Yeah.
And
if
So-
you have like a superconductor with a large Hall response, is that what you're saying?
Yes.
So that's
Yeah.
equivalent to
Yes.
having
So there's
a finite
very
size
small-
wire.
So,
Where in my runners they have an exponentially
so
decaying wave function.
very frequently,
They
the
actually
right
do
way
have
of thinking
that
about
level,
those
but
kinds of
it's
things
exponentially smaller than a wire.
are in terms of not
So it's the same kind
Hall
of-
responses,
Mhm.
but in terms of right and left polarized light.
Yeah.
So it turns out to be simpler.
And sorry for being a little
Uh,
confusing on this.
So
now time.
then in fact it's you have
Sure.
imagine you have a superconductor that has a spontaneous breaking of time reversal symmetry, and then
I'm
you'll
also from
have
Penn State, but I'll be
transmission through the sample for right polarized light will just be a number times the incoming electric field, and the same thing for the left polarized light. So when you start looking at x's and y's and x dash, x, y's, and everything becomes much more
Okay,
complicated.
so same.
Yeah,
But
yeah,
if you, but you certainly
So,
would get
I have a question about the classification.
light when
So
it's,
after
if
you
you
like
go through
you
a pole,
come out
you
like
have light which is
MD
polarized,
and
linearly
high end,
polarized, and
and
it goes through the
so
sample,
will the
it
classification
can
be
be
like
rotated,
rotated cross
but it can also become elliptical.
Okay.
I see.
Yes.
And
So
so
they
it's
are
the sigma
independent
xy
completely.
leads to
They
the
are
rotate,
independent, yes. So you can
real part of
I
sigma
think
xy
that's
leads to
right.
a rotation.
Okay.
The imaginary part of sigma xy.
Okay. And I'm
There can also
thinking,
be imaginary part
it seems to me that this is
And
like
that leads to ellipticity.
topological
So the
filter
light
is also
which is
protected
linearly
by
polarized can
time
become
transition
elliptically
symmetry.
polarized when it goes through.
Yes, to a degree.
So you wouldn't expect
So
like
there is
any
a quasi-periodic
technical
potential.
difficulty,
So this is a quasi-periodic
on,
time.
like conducting this kind
Yeah.
of system for.
Yeah, okay, so if we,
for
I'm wondering that if we
Technical
say somehow
difficulties in doing
interpret
measurement?
this like
Yes.
a time transition symmetry.
No,
Can we use the
not
Q
really.
theory
So
to
I'll,
classify
tomorrow I'll talk
all
about
this?
doing the experiments on topological
Yeah,
insulators in
I
a regime
think
where
one
all
can
the
do
transport
that
is
to some
quantized.
modification.
Yeah.
And,
Okay, so people have.
and so in those systems you have
Well,
very
yes,
small
so
dissipated
Young
response, but large Hall response on the same surfaces. And so you get there you get the Faraday rotation, which is the rotation of polarized light as it goes through the sample,
Yeah, dimension, you can
is
see
quantized
there's some
units
kind
of
of a
that
dimensional
structure.
reduction story here.
Oh, okay.
So
we're going with
if
that
you could
direction.
measure,
Is that not,
so we
I
do, in my group, we
maybe
do a
that's
lot
what
of this sort of
Dominic
time
Elsa
domain
did?
Terahertz
Yeah, so
spectroscopy. And the
Dominic
advantage of
Elsa?
that is that you really
And
measure
so
these
they have
complex
a
transmission
paper out
coefficients
there on
directly. And then,
classifying
you know, so if I have,
SPTs with time
uh,
translational symmetry.
I
Uh-huh.
have,
Is that-
But this is
Good.
just time, but they have time translational symmetry, right?
So
here
if,
there's
so I wrote
time
down this Jones
translational-
matrix before, right?
It's a
And,
reduced symmetry because you have
I might write TXX, TXY,
Did they do that?
No, I don't
TYs.
understand. What do you mean?
So when you have multiple frequencies and
TYY,
they're
so
incommensurate, you
TYY.
don't actually have time translational
Okay,
symmetry.
so there's no time translations.
No, but there is like time translational plus a
And
shift.
let's say,
you
I
can-
have some electric field
if you
like
shift
this,
the
that's
relative
purely
state,
polarized
you
along
apply-
X, and then it
So
comes
you
out on the other
translate-
side,
It's the same like having another
It's
system,
X,
it's slightly
X,
shifted. With,
TX, Y. Right?
let me explain this a little better.
I can take
So
this,
if you have
and
the two
if
drives,
it
omega
breaks
1,
time
2,
reversal
omega 2,
symmetry,
right? So
and
they're both zero,
has, let's say,
zero
some
time.
other symmetries like
And then they
rotational
evolve in
C4
one
symmetry or
way.
something like that,
Nice.
then
So
it turns out that
zero relative to the other
TX
time, you have different
Y
phases between the drives.
equals minus
You can say that
TYX,
this,
and then I can
if you translate, let's say,
transform
100 seconds,
this
right?
to a new basis
It's the same,
where I have
so you
TXX,
get
or
a
right
system that's the
TXY,
same as a different system where time equals zero instead of having the two phases being the same, they had some phase difference.
X minus I TXY, and then I can work in a different basis
It's
where it's
like,
all diagonal.
the system doesn't return to
Right, so
itself.
TR, TL, 0,
However, you can say that there's another parameter, say
ER,
phi 1,
EL,
which is the phase
right,
difference
and then,
at time zero between
Sorry, what was I?
drives.
What was I?
So
just
the time
lost my train of
translation
thought.
of
What was I
symmetry
explaining before?
becomes symmetry.
You had asked-
incorporate this phi one changing.
Large hole.
Okay.
Yeah, large
Shift by
hall,
phi
right?
one each
So,
Yeah. So there's some non-trivial shift of phi.
oh, I remember what
I
I
think
said.
it has a name.
Yeah, so
Kind of things like a
once you
phase
can
on.
do this, and you
what?
can basically
Phase on.
take, you know, this XY matrix, and you can put it in whatever basis you like then.
Nomenclature
As soon as, if I do a conventional optical experiment, the thing I generally can find out is the magnitude of these things.
the states change.
And then,
zero modes.
this quantity is complex, this quantity is complex. When I get the magnitude, I lose all this information, and I cannot put it into right and left. But as soon as I have the complex
Magnetic
quantities,
translations.
then I can put it into
Yeah,
whatever
so
basis
it's
I
a little
like,
bit
and
like
then
a
there's no
magnetic
technical
translation.
difference.
In fact, this
Because
maps
the
into
motivation
the
was
Kramer
in
model.
fractional quantum Hall.
That's
There
right. That
is
is
a
the
transition to
So
the
it's
Wigner
like a
crystal
2D
step.
Yeah, so to the outer,
one
with the
suspected
fluxes,
that
it's not rational.
some
Oh, I
gap
see. That's
similar to
that's
the
why I call it
magnetoroton.
phase.
It's
Yeah.
not magnetoroton.
Yeah.
The gap
Maybe
closed.
so
Yeah.
for
It's
the
kind of similar
magnetic
to the
translation
roton
required
gap
that
in
your
the
flux
helium.
would be
So
some
I don't know
fraction, some
if
nice
Yeah, I know
fraction.
there's
their
a
experiment
Yeah.
can
Okay.
do that.
So this would correspond to
I mean, those
I-
roton minima are all at finite
You don't have
dimension.
any nice.
Right?
Yes.
So that's hard.
That's interesting.
So it's, that's why the symmetry
Yeah,
is
but
not there.
in a quantum Hall, it's not the
But
finite
it's having
momentum.
close. That's what you can do. It's
Okay.
close.
That's different.
So,
But
but I'm not sure if Dominic.
yeah.
Oh no, I don't think
that's
they.
what
Not that.
might be
Yeah, well, it's an
interesting
interesting question.
to
I'm
look
personally
at,
not a very good classifier.
But another problem is in the
Is it very
experiment,
common?
the best samples are in the gallium arsenide.
Yeah.
I don't
Anything else
think it's
that-
convenient for the
I have a question about the quantum novels.
like because it's a quantum well
So,
in a thick sample.
Yeah, so it's
in
not so,
a
I
one
mean,
and two
all the
curves,
multi-layers are
it's
complicated.
moving in a straight line.
Yeah.
Many times they'll have a metallic
So the-
layer on top for gating.
Yes.
This is all-
Yes, but if people have graphene,
So
Yeah.
Can
then
I
and they can
understand
do that
as the real space
fractional
in
quantum correlation, maybe
Yes.
real
Yeah.
quantum
One of the
anomaly?
difficulties for
Yeah,
our
this is
experiment is
exactly
that
So
we
it's
need generally
only
large
one
wavelengths.
sample.
So the wavelength
No,
of
so the sample
terahertz is
itself
millimeters.
is
Yes.
2D.
And so
However,
the sample
because
has
of
to be at
force,
least this big.
since your system conserves energy,
So
your force
this
is
has not been problem,
perpendicular
you
to
know,
the force.
all of this beautiful quantum
So
Hall physics.
if
Yeah.
I,
Graphene, you get tiny
line
little
along this and
100
moving
micron
in this
samples or
direction.
something like
Yeah,
that.
Yeah,
so you think about it as like
It's
an
very
edge.
hard.
And that's
We haven't been
pretty
able to
correct.
get involved with
But,
this.
uh,
at all. I wish we
it's
could.
not
around, okay.
Yeah, it's just the direction.
So
of
someday,
motion depends on
maybe
whether
somebody will make
the
high
top
mobility
or the bottom.
graphene that's a
But
few
you can kind of
millimeters
think of
across,
it that
and there's
the
all
top
kinds
would
of.
be on one side, the bottom would be on another.
Is that true?
But it's not,
Sure.
the better analogy is like you have, you know, in a quantum hall, thing, connect one side, so you get a Corbino disk. Then you can think about putting an electric field along this disk using a changing magnetic field. Then you will get current between the inner and the outer edges of this, right? But there's no edge state associated with that current. Right, so, you have a disk, okay, you change the flux in the middle, and then you have an electric field that looks like this along. There's no edge state that connects this to that.
It's purely from the bottom.
Exactly. So that's the better analogy.
Okay.
There's no real edge. It's just that there's this force, and you get motion perpendicular to it.
那我们要去跟一个 collaborator talk，
So
大概半个知道1个
for
小时。
now I have
现在还早。
对，你要吃饭还到时候
stream and
你微微上叫。
frequencies.
对，
What determines which frequency I absorb and which
Whether it's in the top band or the bottom band.
I see.
Because the top band and the bottom band have opposite churn number. So if you initiate the spin like downfield, like a low energy state instantaneously, so it's like at any given moment there's a magnetic field. So initiate the spin along the magnetic field, it will pump one way. But you can initiate it into the excited state, and then it will pump the opposite direction. And you can control these with like, because the frequency is small relative to the Hamiltonian, you can use pulses of like higher frequency light to make these transitions.
Question about fermion. When you say like we can drive them with like different frequencies to get many kind of them, like what is like the physical picture? Because like if before we have some kind of pairing in the bulk, right? That was just one kind, two of them at each edge. But this one, it seems like there's more than one at each edge. Yeah.
That's right. But the way I constructed the Hamiltonian was using two superconductors with different voltages. Right, you can imagine having like a spin-orbit coupled wire with proximity from various superconductors. And then each one would be at a different voltage. And so the intuition was that each superconductor, I think probably it breaks down after like 2 frequencies just because your space is too big, so you might not have this Aubrey-Andre localization. But I'm not 100% sure. But just with 2 frequencies, you have like 3 superconductors, one grounded, and then 2 voltages to the other superconductor. So the picture was you have a wire, and then superconductor is grounded, and then you have another one that has delta E to the I omega 1t. That means 1 voltage. And then you can have another one that has room to draw. It's like delta E to the 2I omega 2t. And then the thing is, like, each one of them can have an omega over 2 type Majorana, which is like EBI over HR. So I think the picture that one should have is that the superconductors, they produce kind of spectral gaps, right? But now they produce the spectral gaps at different locations with energy. So this is energy, this is density of state. Right? And then, so this spectral gaps is where you can get your Majoranas. And then they're associated, so the spectral gap is associated with the pairing. So it's really like Majoranas that are associated with a particular pairing here. Yeah. Does it make sense?
Yeah. What surprised me is more like if I just look at the chain, like before we break down like one complex fermion into 2 Majorana fermion, and before just like, okay, let's say we're gonna pair them, and yeah, to me it does feel like there must be some kind of like, I don't know, weird pairing that gives rise to like more than one Majorana fermion at the edge. That's how but maybe that's a bad way to think about it.
I don't know, like it might be a better way to think about it, but this is just not how it's not how I thought about it. I mean, for us, it was just like, you can have an index, like a Z2 index next to every breaking, next to every, gapping. But you know, we were kind of, I was involved in this work 7 years ago. We discovered this by Majoranas. I was surprised by it. It's like, oh, neat, it's a great effect. But we didn't expect it. It's just like, oh yeah, there's another particle symmetry. There could be another Majorana. We had an example. But that surprised me.
I don't understand the importance of particle hole symmetry here.
You can only have Majoranas in particle hole symmetric parts of the spectrum. Because Majorana is real, so it should not change.
The Kitaev chain requires particle hole symmetry?
It is particle hole symmetry, it's a superconductor.
But particle hole symmetry is not a unitary symmetry.
It's anti-unitary. That's why the fact that Majorana is invariant is because it's a real thing. It always has to be like a particle and a hole, combination in equal things.
Lucas calls it intrinsic. It's intrinsically topologically ordered, so it doesn't require any symmetry. Okay, tell me it does. Okay.
I think automatically when you write PDG Hamiltonian, you should have particle symmetry of some kind. Just because it's the BDG Hamiltonian gives you ladder operators that creates excitations, right? But there should be associated ladder operators that remove those excitations. So in the context of that Hamiltonian, it looks like particle and hole being symmetric. But just the fact that you have C dagger and C, and yeah, you have to. One has to have positive energies, and the other has to have negative energy that are the same. But it's just because we're writing, maybe it's because we're writing a second quantized Hamiltonian in terms of like first quantized. first quantized orbitals have to have particle asymmetry, I think. Here, do you have dinner plans?
No. I was finding out what you were up to.
Yeah, no plans.
Okay.
Any particular time?
No, I was going to walk over to the Nassau Hotel, possibly go for a run or something like that, and then
Yeah, ping me after the run.
Yeah.
I ran in the morning.
you're right around. Okay.
Yeah, I can recommend. You know your way around here, right?
Yeah, at least enough for that. So yeah, what are you staying till when? Till tomorrow morning or something?
Tomorrow morning.
You have a flight tomorrow.
8 o'clock from Philadelphia.
Okay.
8 o'clock.
Do you have a moment to help me fill in some?
Sure. Do you have my number here?
No. Let me get that. So what do you think? 6:30?
Yeah, that's fine. Whenever you come back for the
Yeah.
run.
Okay.
Let Nassau.
So mine is 410-530-7882.
Wait, so 410
530
530.
7882.
Got it. Okay.
Look, apparently.
Yeah.
Okay.
Who knew? All those March meetings and ASPEN meetings.
Yeah, I think it probably was. I need to look for my lecture notes. We went camping this weekend, and then I was like, last night, I was like, okay, let me get my lecture notes out. Like, oh crap, 11 o'clock last night. But I found them.
But you didn't need to write them from scratch.
No, I didn't. That's why I was. That's why I freaked out. Is because I was assuming that they were like where I thought they were, and they weren't. So.
Did you go to the Cornell school just a few weeks ago?
Yeah, in June or something like that.
Yeah, I was there on the theory side.
Oh right, that was going on. There was a thing going on at this. That's right. You were. I think you were. You might even.
Did we run into each other? I forget.
No, but I came on Friday. I think your guys' school was the first week.
Yeah, that's
and
right.
I arrived
left
like
on
Friday afternoon.
Yes.
Yeah.
I drove down to. No, I left before. I did in the beginning. No, I left on Friday to drive down to DC.
Yeah, that was Epic's run. Or was it?
Yes. Yeah, so 6:30ish, but
Okay.
I'll just right here from you.
You're also at Nassau.
Yes.
Okay, cool. All right, see you later. See you guys
See you.
later.
Yeah, okay. First, I don't quite understand the distinction between the weak drive and the strong drive.
Mm-hmm.
Of course, okay, omega's big or omega's small relative to V, but
So there's no strong distinction, just that the red curve that I showed on my slides, it's like very broad or very thin. So it's a question of like, so the two drives, it makes a big difference. So if you, let me do it, just right with that. So this is the, say the integer of distance. For weak drive.
no, sorry, what's N1 and N2?
So the number of photons taken from.
Yeah, I didn't catch that much.
Okay, so if I write the time-dependent wave function, e to the minus I n1 omega 1 plus n2 omega 2 t, right? Psi n1 and n2, right? This is like a general expansion of the psi. These guys can also depend on t, but slowly, right? And what I said is that now I'm going to treat this as my wave function.
Okay.
And write down the Schrödinger equation for this psi n1 and 2.
Uh-huh.
So that means that like I can write the lattice n1 and n2. Each point in the lattice is described by a wave function. So it's like you have a particle.
Those are supposed to be eigenstates of the flow K
No,
operator.
no.
The psi n's are.
No. It's just parametrization. I can write anything like this. I didn't say anything, right? I just said that I'm expanding in harmonics, and that I have a time-dependent coefficient to the harmonics.
Okay.
I can describe any function like this.
Okay.
It's like let's do it in one dimension. So if I just have a single drive, here it's nice and clean. So H naught plus V cosine omega t. involve it in harmonics. So it would be like sum of harmonics of the drives of this drive times some functions psi n, which themselves can have, say, a slow dependence on time.
And you haven't told me anything about psi n.
No, I didn't tell you anything about psi n, but what I said is that this has to obey Schrödinger equation. That's the one restriction. Sure. So I'll put it in Schrödinger equation and separate it to harmonics. And then I'll get deep psi n dt equals h naught psi n plus this v to create hoppings.
I'm confused with this rewriting of psi. This is so general. I could just like.
Yeah, it's completely general. So the only restriction I would say is that the spectral weight of this psi n of t should be smaller than omega. And so it should be 0 at frequency smaller than omega over 2. So this would be slow moving.
Okay.
Relative to omega. Just very slow oscillations relative to the drive. And then I can just stick it in the Hamiltonian and it looks like this in the Schrödinger equation. Just that's what I'll get.
What do you have psi n minus 1? Oh, okay,
Because these guys promote.
You chose a particular.
Yeah.
Hamilton.
Right. Yeah, in general, it would be the harmonic. You know, you can put like an M here, like a GM here, it would be the one in the Fourier series.
Okay.
Right, but this describes just a particle hopping on the 1D lattice. Right, so
Yeah.
this is like N, then I have two sets, and I have hopping back and forth with V. I have an on-site Hamiltonian, and I have a force.
So that's your synthetic dimension.
That's the synthetic dimension.
Okay.
And then the question about weak drive. So I could have done it for the weak drive as well, right? Except in the weak drive, omega is so large that you're restricted to one of the sites. Like you can't move like this more than one or two sites. It doesn't make sense to call it a synthetic dimension. So in that limit, you can actually say, well, let's get an epsilon psi n, right? And solve this kind of big matrix equation. But now, this v is small, right? This omega is large. So, it's like, in terms of energies, right? I have 0 photons, I have 1 photons, I have -1 photons.
This is weak drive you're talking about.
Weak drive, so V smaller than omega. But V has this scale. So you want to use V to excite into 1. That's like a very big energy mismatch, so you have to come back. Unless you have a resonance. So I can draw the dispersion around each photon number. Right. I can draw the dispersion like this, right? And now, if the dispersion is sufficiently broad, such that actually there's overlap, then you could actually have a resonance. And this is how you can live the overlap of two sides. But if you don't have a resonance, there's no chance. So there are three, I was always pegging two energy scales to each other. But there are actually 3 energy scales. There's the bandwidth of the time-independent Hamiltonian. There's the strength of the coupling to the light, and there's the frequency of the light. And all those 3 can be strong or weak relative to each other. But I was usually pegging 2 of the 3 to each other. Like in the weak coupling limit to the fast frequency, fast drive, I was pegging omega to be roughly of the same order of H0, so that you could have these resonances. But I didn't make things go of the same order of magnitude, and V was smaller. And in the strong drive, I had omega small, but the drive of the same order as the Hamiltonian. So the two limits were H0 and V, much bigger than omega. So it was like strong drive or slow drive, right? Saying the same thing. And then in the other case, I said that H0 and omega are much bigger than V. You don't have to do that, but it's simplified in the way that I was discussing things. And if H0 and omega are of similar magnitudes, then you get these resonances.
You have this effect on the band structure, regardless of whether it's strong or weak drive.
Yeah, but I mean, look, I mean, if you have a strong drive, you have a band structure that's completely different than H0. Look, so you introduce the drive, right? V is of the same order of H0, right? So H0 is going to change. But now if you actually make this effect on the spectrum, you start making copies, Fourier copies. So Fourier copies are like, very thin cut slices of your dispersion. So if you really choose to do that, you end up with the following thing. Take just a parabola, like a free particle. Now I start driving it. Here are my Fourier zones, omega, etc. So you have to copy this here and this here, so end up with things like this. It's kind of a little crazy, right? Then if you have like another band, right? Then you copy that too. And so that's so many crossings, like completely different band structure.
Yeah.
So that's why it doesn't make sense to do this, and it's better to. So for that reason, we can find a lot of eigenstates like that. But their energy will just be in some range of a very small omega, so it doesn't actually give you so much information. So for that reason, it's better to think about the semi-classical.
Okay.
Does this make sense?
Yes. Yeah.
So I mean, it's not like the phase transition between one and the other. It's just for the large, so strong and slow drive, you're confined. Sorry, strong and slow drive, you can spread out over a big chunk of this. But fast drive, you're really confined. It's one or two. Now, if you spread out over a big chunk of this, if you're just looking at Fourier eigenstates, it's like you're saying, okay, so now let's look at the energies that are just confined. Just choose this as the zero. It's confined from here to here, right? Because like it has to be between plus omega over 2 and minus omega over 2. Actually, your wave functions are spread out over this whole n. So you're losing a lot of information by just confining yourself to this eigenstates. So any initial state that you think of will actually be expressed as many harmonics. So then it's nice to figure out what the harmonics is. And what they're doing is they're almost like a free wave. And what this motion back and forth is in a way it would be, it is Bloch oscillations of a lattice. But in this context, you can also think about them as Rudabeh oscillations. Right? So you start off at some state, then you break it apart into all the Fourier eigenstates.
We're bouncing back and forth. We're talking weak drive.
No, strong drive. So I'm saying in strong drive, you could think about like doing these Fourier eigenstates.
Yeah.
And I'm saying it doesn't make sense, but what would happen is that if you start off in some state, you will. So it's a spin half. So you only have like two Fourier eigenstates, right? You have some combination of the two, right? But each Fourier eigenstate is spread out over n so much. Now you do Rudabeh oscillations between those two states. But because it's spread out so much, you get your particle kind of bouncing back and forth on this n space quite a bit.
But we already said if omega is large.
Yeah. Suppose omega small.
Omega small. Okay.
Omega large, you're just here.
Yeah.
And yes, you can have Rudabeh oscillation between having a photon and not having a photon.
Yeah. Okay. So then, in the example of the drive chain, there you have weak driving.
Yeah.
Okay. And then I missed your explanation for why you have some Majorana mode at the point where.
So I do completely explain it, but I just showed kind of circumstantial evidence that whenever you have like a gap closing, so you have a gap closing, you have a gap. If all phase transitions are topological phase transitions, then one of the sides should have a Majorana. Now, for the Kitare model itself, the reason why there was a Majorana there is because you do go from a situation like this to a situation like this. This is topological. You remember what these things were? Yeah. So with the drive, I mean, it's harder for me to make those diagrams, although probably there's a space which we can make them. But this also measures the Fafian. Okay. And you can measure the Fafian of U. And you can also measure the Fafian of U squared. And U squared, if you have like 5 Majoranas, there'll be Majoranas after 2 periods. So every time that the Fafian vanishes, you know that you have a phase transition. Right? And what I calculated is where the Fafian was vanishing. Because the only place that the Fafian can only vanish or change sign. So really the sign of the Fafians, right, gives you the topological index, right? Okay. So, and the only thing that can change the sign of the Fafian is the contribution from k equals 0 or k equals phi. Because those are the only momenta that don't have partners, like a squared. Yeah. So what I calculated is where those things vanish.
Actually, I have a question. You talk about some localization because you're going to get a bunch of neuronets, and you say you can hybridize with stuff.
Yeah. So I was saying that you avoid that because of localization along the semi-conserving line.
Yeah, can you explain like a bit more about that, like about the localization?
Yeah, so if you have like, so there's a standard model that's called the Aubrey-Andre.
Is it the one with like incommensurate like potential?
Yeah, exactly.
This one, I see. You can look, that picture is exact. Okay.
Exactly.
Nothing from it.
But you can also do it with like two potentials.
Mm-hmm.
So in our case, you can think about one lattice as being the lattice and the other being the potential. So two-dimensional space like that, right? Mm-hmm. There's some line that cuts across. Right. Now we'll connect these the points that are closest to this line. Now you can think about this as an index, and then in every n1, right? You can say that the potential is just the difference between this line and the points. That will be the same. What?
Some quasi-periodic potential.
Yeah, but then it will be exactly like the Aubrey-Andre. So it will be case and plus 1. And then plus h cosine kn. And then this is a self-dual model, so when h bigger than j, if I have a 2. And the self-duality is just like you can express this in momentum space, and then this would look like a quasi-periodic thing in momentum, and then this would look like, yeah. So you just say, sorry, not k here. Yeah, so this k is not the momentum of the particle, it's just a number that you put in. Mm-hmm. So then you can make a series of momentum k1, k2, k3, and k1 is say 0, k2 would be like q, 2q, etc. And then the series of momenta eventually will cover all your gluons, huh? But the kinetic energy, right, would be cosine of this object, so that would be like cosine mu q. That's the same model. But anyway, so the point is that the Majorana that we calculated was due to some hybridization because of a single photon, right? And maybe there's another bulk state that's there at a different energy, but you need to take a few photons in to make up for the energy difference. Maybe one's like 5 omega 1 minus 4 omega 2, something like that. And then that means that we need to go to some other place in the synthetic dimension over here. But this motion is prohibited because of this localization. So that even though energetically you can make this transition, like the Hamiltonian does contain the terms, the coefficient of the matrix element is exponentially small. So that's what allows this transition. So yeah, that's our understanding. Then we did numerics to see that this argument is actually borne out. Does it make sense now?
Yeah. Right. Okay. Thank you so much.
Sure, it's a pleasure. I hope I didn't tire everybody way too much.
With a fear mode, it's like the time constraint. I feel like it's not enough. Just 2 hours, I think, with 2.5 hours.
Yeah, it's 2.5 hours. So 1.25 is kind of a weird time because I think you either program to give lectures that are 1 hour long or 1.5. 1.5 is really 120, 125 plus question. I don't know. I realized I was packing a little bit extra. But I thought it would be more fun, but maybe not. Hey, enjoy.
Thank you.
Sure, and like I said, it will be notes, and drop me a line with questions if you want. They won't be here tomorrow, but I'm accessible.
You know when they'll be posted? Did they tell you?
I need to make sure that.
Be emailed or something.
Yeah, so they'll just email it. But I need to finish it. I need to put the figures there and stuff like that. So it'll take me a day probably.
Otherwise, I was once at a talk on diet chains, and a senior faculty member complained that Majorana's had been understood from the classical Steinbeck perspective a long time before. Do you know this story?
No.
Okay, yeah, me neither.
Who was the person? Do you know?
Yeah, Lawrence Yaffe. He's at UW. So apparently, because of this correspondence between 1 + 1D quantum systems,
And yeah,
you can
and
talk about Majorana model, Majorana modes, and
yeah. So the question is, okay, so why didn't we do this experiments with indium arsenide wires 60 years ago?
I suppose, but
No, that would be the question that would raise. But it's true. I mean, you have Majoranas there.
in 2D, in some 2D Steinbeck system. Do you know what that
No.
system would look
It's
like?
an effective. It's an Ising model. Just an Ising model.
Then what's the Majorana mode?
If you look at the conformal field theory that describes the critical point of the Ising model, it has right. So this is a long story.
Okay.
But knowing renormalization group, etc., we know now that critical points are associated with a diverging length scale, right? So that means that correlation functions in the critical point have to have no length scale. And then there's like a leap of faith that says, well, in that case, in 2 dimensions, actually having no length scale might imply a bigger symmetry, which is conformal invariance. And any analytical mapping of your space to itself should leave the theory intact. That got upgraded to conformal field theory. Now you can have, so if you want to make a field theory out of it, it's like shitloads of symmetries, right? And they put a lot of constraints on the field theory, so it gives you conformal field theory. In the conformal field theory, you can show that the number of operators you can write is restricted.
Okay.
So you can think of this, so even in the statistical mechanics, you can make some operator. For instance, you can flip a spin. You can think about it as an operator. You can make a chain of flip spins. You can make a wedge, right? So all those excitations that you can imagine making, and there are some that are low energy excitations, right? And now you can also think about like mapping this to 1 + 1 or not. But conformal field theory is kind of like describing the evolution for one-dimensional system in imaginary time. And now there are constraints on what are the primary operators. So the operators that are local that give rise to all other operators. And in the Ising model, Majorana fermion is one of those operators. So there's an operator called sigma that has the right kind of properties. But in the conformal field theory perspective, I think people knew that it's like
It's local,
well,
or is it just?
It's local in some description of the system, the same way that my Majoranas were local in some description.
Yeah.
However, in other descriptions, there might be string operators. But unlike, actually, there is a very strong sense in which my Majoranas and these Majoranas are different. But it is true that the Ising model has these Majoranas in it, and they have this scaling dimension of like 1/16, sound neutral. If you can really calculate this, then you find that the scaling dimension is 1/16.
Scaling dimension.
So the scaling dimension is kind of like the energy eigenvalue in the conformal field theory. But the idea is like if you squish your space by some factor, how much would that operator squish? Or another thing is like if you have two operators and you calculate the correlations between them, the correlations fall off algebraically, and the scaling dimension dictates the power. Because you know, if you have like 1/L to some power, then L goes to like L over B, then it should be like suppressed by B to some power. And that power is the scaling dimension. So the correlation is twice the scaling dimension. And I think that's what this person meant. Just the sigma operators, they correspond to Majoranas. Now, if you have a two-dimensional Ising model, which corresponds to a one-dimensional transverse field Ising model. So by the way, in the transverse field Ising model, this 1/16 has a very specific meaning. If you can, try to calculate the correlation between sigma z in the transverse field Ising model at some distance. You'll find out that it's hard. I think Subir does this calculation in his book. And you find out that the correlation falls off like 1/L to 1/8.
Not 16 though.
Well, it's two operators.
Right.
So 16 times 2. If I remember this right. But it's the same system. It's just at the critical point.
But then in the fermionic system, I guess it doesn't make sense to talk about the correlation of just 2 Majoranas, does it?
You can.
And does it fall off like 1/8 as well?
It should, the same model. But what I want to say is that you cannot do braiding. Like intrinsically, you cannot map a two-dimensional Ising model into a wire network that allows you to braid Majoranas.
Okay.
So that's
that. Physically distinct in that sense. Yeah.
It's physically distinct, but you know, there's a lot of science that came out from this question of braiding, which was only I think people only started thinking about it after Reed. Thinking about Majoranas in a two-dimensional quantum Hall state. So, I don't know. Like Yofe is probably Russian, right?
What was this?
Yofe, Lawrence Yofe, you say? No.
I don't think he is.
So not Russian.
Well,
yeah.
He hides it if he is.
No, the Lawrence is not Russian. No, I was saying like it's a very Russian thing to say that, oh, this system is exactly the same as this other system, so there's nothing new here. But it's not completely true. Like what I said, there's nothing really new. It's all non-interacting driven systems. And we were just putting pieces together in a different light.
Yeah.
That shows that you can get very different effects, like this frequency pumping effect. It's very different than having Hall conductance of electrons. It's the same model though. We just mapped it to different variables. But it inspires different experiments, basically.
You made a quick comment about this being a time crystal. If I were just Jordan Wigner to transform your models, do you get exactly the time crystals? That's exactly the same model.
And that Majorana at omega over 2, that's pinned to omega over 2, is why it's robust. Like no matter what you do to the system, the only place you can have this Majorana is at omega over 2. And that's why the system will always respond at half the frequency. So, yeah, I think the Shivaji and company, when they discovered this kind of behavior, they didn't realize this correspondence, and they did it independently. But then after looking at the papers, immediately say, well, yes, of course, it's this thing. It's just a bigger transport. So, we did our share in pointing it out. But it's not like it's another example. It's not like saying there's nothing new.
Yeah.
Right, but it's there's a strong relationship, but every statement of the problem always gives rise to like different ways of realizing the system and manipulating it and figure out new physics. So yeah, I think that's I gave you the story that connects it to the Ising model, right?
Yeah.
Yeah.
All right.
It's a problem, we're in condensed matter, right? So this period where we were discovering topological behavior was a very unusual period, where there were a lot of new discoveries that were pretty unrelated to previous things. That's not the norm.